I will be discussing the problem linked list cycle. The problem statement says given head, the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS is used to denote the index of the node that tails' next pointer is connected to. Note that pos is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. So there are two approaches for solving this problem. First one is we need to start from the beginning of the list and then keep going traversing through the list. If there is null after last element, then we will know we reached at the end of the linked list. In that case, we return false or no cycle is found. We will never get null if there is a cycle. We maintain a hash map. We take every single node and we take the node itself and add it to the hash set after we have visited the node. We can add the node because the node itself is just an object and we usually can hash an object. If we notice that the node is already on the hash set, that is we are visiting the node twice, that obviously means there is always a cycle. Then we return true. The solution code, starting from head, it checks whether the current node is already in the visited set. If it is, that means the list has looped back to a previously seen node so a cycle exists and we return true. If the node has not been seen before, it is added to the set and traversal continues using the next pointer. If the traversal ever reaches none, the list ends normally and no node was visited, so the function returns false. Each node is processed once, making the approach linear in time, and the set allows constant time checks for repeated nodes. Space complexity of this approach is big O of n, and time complexity is big O of n. There is one more approach where we can actually optimize the space. That algorithm is called as Floyd's tortoise and hare algorithm. The solution, the algorithm says that we will use two pointers, slow pointer s and a fast pointer f. Slow pointer is just going to be shifted by 1 and the fast pointer is going to be shifted by 2. When both the pointers meet each other, they were in a cycle. That is always going to be the case in linear time. On a single iteration of the loop, the distance between the pointers is being closed by 1. The solution code, slow pointer advances one node at a time, while the fast pointer advances two nodes at a time. If the list has no cycle, the fast pointer will eventually reach none, the end of the list, and the loop exists, returning false. If a cycle exists, the fast pointer will eventually lap the slow pointer inside the loop, causing both the pointers to point at the same node at the same time. When it happens, slow is equal to fast becomes true and the function returns true. The key insight is that in a cyclic structure, a faster runner must eventually catch a slower one, allowing a cycle detection in linear time without extra money. The time complexity of this solution is big O of n, and the space complexity, as I said, we are using an optimization approach. The space complexity is big O of 1. So the patterns which are observed while solving this problem are: first is two pointer fast and slow pattern, where if I could say in one line about this approach, we used to use two pointers moving at different speeds to infer structure, detect overlaps or find position. Second is cycle detection pattern, where we detect a repetition in a structure without extra money by leveraging traversal behavior. Third is pointer reference based comparison, compare node references, not values, to reason about structure correctness. Fourth is space time trade-off pattern, where we choose between extra money hash set for simplicity, and then second is mathematical traversal, Floyd for optimal space. Fifth is termination condition reasoning, where we design loops that safely terminate fast pointer hits from none to no cycle, and then pointers collide to cycle exists. Sixth is repetition without storage pattern, where we detect repeated states through movement instead of remembering past states. Seventh is mathematical invariant pattern, where we rely on guarantees from relative motion. Faster pointer must catch slower one in a cycle.